do those. Is Michael N? Michael N here? No. Brian. Yeah. Everyone else got your test back. That's fine. We'll probably be done the lesson by then. I know that's not my phone because mine's sitting home. It's kind of freeing. Like, I have a phone today. Yay. Yeah, that's the issue. Yeah, you missed that. Yeah. That's all right. I'll have to do my job today. So for those who just came in, right now everybody's just working on those two problems, and then we will solve them together. And the evaluations for the course are up in Canvas, so feel free to have fun with that if you choose. Yeah.
She walks in water. She doesn't walk in water, it walks in me.
Anyway. Yeah, I know. You get them for like every class. They're all in Canvas. There you go. That's good. Lucy. Yeah. Well, the upper, you do the top. Yeah, minus the bottom. All right, I gave you all time to kind of look through it, but we're going to do them. Okay. So when you are given the integrals on the test, remember, it's not going to be, hey, these you need to use U substitution on, right? They're just going to be, it's going to be like a good 10 integrals. So they're going to be mixed. They're going to be mixed with definite, indefinite, ones you may need to use U sub on, ones you won't need to use U sub on, ones that you can possibly use the even odd rules on if you choose, if you know them, right? They're all going to be mixed together. So when you look at a problem like this, or like both of these up there, what kind of sticks out to you to makes you think, oh, I'm going to have to use U substitution on this one? What is it about them that do that? Kevin. Yeah, you've got these composite functions, right? They're composite functions. So you've got this outer function. It's a secant squared, right? But then you've got this inner function. And what's the inner function here? 10x plus 7. So it's identifying that. Over here, you have, in this case, was that supposed to be square? That was probably supposed to be. Well, we're going to leave this one as it is. I probably forgot to write an exponent on it, but that's okay, because we're going to leave it exactly as it is. When you look at this second one, do you see an outer versus an inner as it's written? do you see an outer versus an inner? So you can, right? You can say, okay, there's no exponent here, but I can think of this as the inner function, right? Because I have this over here. But, so I kind of tricked you here because I said they were going to give you some u sub to do. What might be, when you look at that second one, do you see that it's harder to see an outer versus an inner? Would the problem be easier to say it's definitely u sub if there was, say, this up here? Now do you see an inner function? Right? Everyone sees it. Oh, 4 minus x squared is my inner function. But it's not there. All right? Yes. Don't forget the most basics. Actually, I didn't mean to put this one up there because it's a good problem. Because when you get them all mixed up, a common thing, because what happens is you learn u sub, then you go take the test, and you want to make everything a u sub problem. Is that really a u sub problem? You can simply distribute and use basic rules of integration. All right, so don't forget that. Even if it were squared, can you all square a binomial pretty easily? Do you have to use u sub on a square? Just do the, you can. Or you can just do the algebra and do basic integration. All right, so just keep that in mind as you're going through the problems. So let's do them. Let's do the first one. We decided the first one definitely a u sub problem, correct? So I'm going to let u be my inner function. So I like to do this. So u, so what's my inner function? We decided it was 10x plus 7. I'm going to real quick just calculate what du is. Okay. There were a lot of questions, and I think I was trying to give way too theoretical answer last class. But technically, some of you were asking, why is dx there? Why is dx there? I want you to think of this algebraically in the most simplest way. If you have du dx equals 10, you can just multiply both sides by dx. So it ends up over there in du itself. Does that make more sense? Think of it that way. It's kind of a more simple way to do it. Okay, it makes sense that the dx is out there on the other side.
Is there going to be a point where we have to rearrange the du equals 10 dx?
We did an example, yeah,
Okay.
in class. It's on, if you weren't here Tuesday, it's on the video.
Okay, thank you.
There is one that, yes, there's a good example in there, actually, if you take a look at it. I think I posted that the other day. Where we did it in class on Tuesday, where you have an x over a radical, and the u is inside the radical, and it was like x plus 1. So u equaled x plus 1. So that means x itself actually equals, if u equals x plus 1, x is u minus 1, and you can replace it with u. And then you have a problem of just u's to integrate. But yes, that was on Tuesday's lesson. All right, let's finish this one now. Once we have everything, now we need to check, remember? So this is where we check. I got to say, all right, here's my, that's there, right? Do I have a du, everybody? What's the only part I have? So what's missing? I can go ahead and stick that 10. I can put it anywhere I want. I'm going to put it next to there so it looks like it's 10 dx. I can do that as long as I do what? Yeah, you can do it as long as you stick it out there. The other thing you can do, because remember, this is math. There's more than one way of thinking through stuff, right? The other way is, I'm just going to write this and then I'll erase it. The other way is to think of it this way. Oh, but dx equals du divided by 10. So I can replace dx with du divided by 10 and still bring the 1/10 out. Same concept, just different ways of thinking about it, okay? I like to do, hey, what's missing? Let me stick it there and let me balance it on the outside with the 1/10. However you want to think about it, though, it's fine. Going to get you the same answer. All right, once you do that, now just rewrite everything in U's. Put everything in terms of U. So let's go back. So now I have 1/10. I still have secant squared, right? 10x plus 7 is U. And 10 dx becomes... So what you've created is a new integral that you can integrate based on what you know already. You know how to integrate secant squared.
Why is it 10 dx and then 10?
So I need the derivative, the 10 dx, right? I only had the dx. So I can go ahead and stick the 10 in front of it. But to do that, I've got to balance that 10 out. Because what's 1/10 times 10? 1. So the only way you can introduce a number, because this isn't an equation, the only way you can introduce a number is by multiplying it by its reciprocal. You can do that anytime. You can't do it with variables, but you can do it with constants. What is the integrate? What's the integral of secant squared? Tangent, right? 1/10 stays. Don't forget, this is an indefinite integral. What do you need? And then the last step. You don't give me an answer in terms of U. If it were a definite integral and we changed the limits, then yes, you don't have to plug it back in. But because this is indefinite, we don't give an answer with U. What is our answer? 1/10 tan. Yep. And again, we're going through each and every little tiny step. You're going to get the hang of this, and you're going to just be able to look at that. 10's missing, tan, and you will literally, at some point, skip all these steps. Because you'll practice so much of it. Right? Right. In Calc 2. All right, let's do B. Now, when we look at B, one of the things we said is, you could actually go through and do U sub. Your inner function is 4 minus x squared. I think it's a longer process because if you recognize it without an exponent, you can also easily just take this problem and make it 8x minus 2x cubed, right? And we can integrate it that way. You're going to get the same answer, so it's up to you what you do. All right, and then this is good because now we're going to just remember basic integration. What's the integral of 8x? 8x squared, I'll write it out, 8x squared divided by 2, all right, minus, what's the integration of 2x cubed? And goes 0 to 1. Don't forget the 0 to 1. And then, yeah, let's simplify it before we put 0 to 1. Lucy? Okay. So 8x squared becomes, 4 minus, right? Good so far? And then plug everything in. Plug in your 1. Yeah, I'll put it in, but I hope you all recognize that because every piece has a variable in it, which, by the way, is going to happen when you integrate, right? You're not going to, you're not going to end up with a constant because all constants end up with an x. That's what makes 0 really cool, because the whole thing just goes to, I always get excited with I'm integrating, and one of my limits is 0, because I know I don't have to do any work for that one. Unless, of course, I'm with trig functions or ln's or e's, then yeah, you got to do the work. But polynomials, we're all good. All right, so what is this? It's 3.5, right? 3.5? 3.5. And we're good. Lucy. What are we trying to find in terms of what does the 3.5 represent? So it's the area. This is a cubed function. And it's a cubed that's negative. So somewhere, I don't know where this function actually is. I'd have to graph it. But maybe it looks something like, I don't know, like that. Okay? I'm making this up. I don't know where this function is on the graph, so I know I have an idea of what the shape is, but I have to do a little more work to figure out where it is. Actually, it goes through 0, right? Yeah. So it's between 0 and 1, it would be whatever that area is. Okay? I know that's not the necessarily. It's kind of close. I don't know. It's something like that. Okay? And that area is 3.5 blocks of grid on your grid paper. That's essentially what it is. So if you actually did graph this and had unit blocks, you would be able to count about 3.5 blocks in there. Okay? Yes. On the second one? Because it's definite. So what happens is, if you were to put the C in, you would have a plus C over here and a minus C. They cancel away. So you don't need to worry about the C's when we're finding the area, when we have a definite integral. Okay? So indefinite integrals are nice because you don't have to do that extra arithmetic work at the end, because that's all that really is arithmetic work. But you don't forget to put the C in those. Okay? We are today. Sorry. I'm in a mood. I'm in a mood because I don't have a cell phone. And I'm going away tomorrow, and I love when I go away from my house. Anyway. All right. So we're going to do it right now. Okay. So I am going to do a little bit from 6.1. I'm not doing a lot because when you guys take Calc 2, those of you who are doing it are going to start right there at 6.1. All right. So, but what the problem I'm going to do from 6.1 is going to be on the test, not extra credit, but you're going to like it. It's a nice problem. Okay. Promise. Then I'm going to do like 1 or 2 problems from 6.2. That will be the extra credit. Okay. And please, it is, of all the extra credits I've given, I guarantee these are the easiest ones. All right. So you can all do this one. Yes. Yes, you'll even have time. I promise. I won't get it in my head and say, oh, I'm going to give them this tricky problem. No, I'm not going to do that.
Problem are treated as calculus. This is your phone. We have to figure it out.
When we're done these 2 problems, we'll do a quick review. No. Straightforward. I'll tell you, everything is going to be on the test in a minute. All right, 6.1. So 6.1 brings us back to integral applications with velocity and all that other fun stuff. And essentially, what we have is position, remember, velocity. Like I said, I'm doing just parts of it. So I'm going to do position, velocity, acceleration. I'm not doing the whole 6.1. I'm kind of skipping around the parts I want to do. So one of the things we all learned, this is what we did in the past, right? We know our position function is s of t. Our velocity function is v of t, right? And the acceleration function is a of t. And what we went over back in chapter 3, when we did, it was chapter 3, when we did derivatives, we started derivatives, we said, oh, well, or let's do it this way. We said at s prime of t, when you took the derivative of the position function, what do you get? Velocity. Right? Okay. If you take the second derivative of the position function, the second derivative of the position function is the derivative, the first derivative, you agree, of the velocity, which is equal to what? That's it. So, all we're going to do is go backwards. Just go backwards.
Very dumb question.
Mm-hmm.
That is gonna bother me thought of asking. Why is position S of t and not P of t?
Yeah, I don't. I don't know the answer to that one.
I'm sorry.
Position is always S. I know. I know. We don't use P of T.
Spot. Okay. Oh, well, okay, thank you.
There you go. Yeah, it's standard. There's a lot of standard notations that are used, and S of T is always used for your position function.
Mathematicians, you can just say every now and then, I'm gonna completely trip the entire world up. Like when it's I like complaining a lot or something.
So, here we go. All right, so now does this make sense? Let's going to go backwards. So we can get our S of t function by integrating which function? The velocity. We're going to integrate it from 0 to t of v of t. Well, let me call this v of x for now. Don't worry about the notation so much. There's one little piece though. When you just do, let's do this. Get rid of this. Let's call it this for a second. Do it this way. The integration of velocity dt. All right. When you just integrate it though, and if it's not definite, if you're not given a time frame, there's going to be this c value, right? We're going to have to be given information to calculate that c value to get the exact position function. All right? And what we're going to be given is we're going to be given like what s is at 0. All right? And the same is going to be for velocity. What's velocity going to be? Velocity is going to be acceleration. And we'll talk about, these are the C's. 0. Or V. V, sorry. Oh, I wanted that one in blue. Okay, these are essentially your C values that we're going to talk about in a second. All right? So again, I told you this problem was going to be easy, right? So let me go over what you'll be given. So what we're going to do is position and velocity from acceleration. So if you are given a sub t, and you will need to be given v sub 0 and S sub 0. If you are given all of that information, you can actually come up with your velocity function and your position function. Okay? Not even that hard. All right? So let's do one. Let's suppose All right, so let's get started. All right, so first thing we want to figure out is V. So let's do, we need the integral of AT. So I want the integral of negative 32. So what do we get? So we would get negative 32 T, correct? Technically plus C. Everyone agree? All right. So given this information, what we've done before is we said, okay, I know V of 0 equals, right, so V sub 0 equals negative 32 times 0 plus C. This is how we did in the past. We plugged in the 0. And what do we get for C? You can clearly see C is what? Yeah. So essentially what we're saying is you don't even have to do that much because we see it right here in the formula. All it is whatever plus whatever V sub 0 is. So yes, you are just adding 70. What we've done in the past is gone ahead and said, all right, V sub 0 equals 70. So I'm going to go ahead and plug 0 in for T plus C, and I'm going to solve the equation for C. Well, that automatically goes to 0. So what does C become? Your 70. So this is just like a shortcut saying, yeah, you don't need to do that. If you know V sub 0, just add it on the end. That's it. So what is my velocity function? So V sub T equals negative 32 T plus 70. So it's not different than what we've done before. As long as you're given V sub 0, you know automatically that is your C value. Lucy? Say that again? VT? Where's DT? Oh, that's just, so the reason the DT is just telling us what we're integrating, what's the variable we're integrating with respect to, that is where we get negative 32T from. If it were a dx, you'd have negative 32x. If it were dy, you'd have negative 32y. That is just letting you know what the variable is you're integrating with respect to, which is really helpful when you're integrating a constant, because without that piece, you have no idea what variable to put there, right? Okay. So now we have our velocity function. You're going to do it one more time to get your position function. So for my position function, but now I understand the concept of where the C is coming from, so I can just use the formula, which basically just states I'm going to take the integral of the velocity. And I'm adding your S sub 0 position, which is what? Yeah, you're adding whatever S sub 0 is. Remember, this is that C value, basically. Okay, so in this case, what am I putting in there at the end? 10. So after you integrate it, you're adding that 10. All right, so what is the integral? It's negative 32t what?
But you're not integrating 10 itself, right?
No, that
So why
is,
is that?
it's here. Is that better?
Oh, okay.
I'll put a parenthesis around it for you. Yeah, they don't have the, in the textbook, we actually put them first, so it doesn't look like it's part. The integration stops as soon as you see the dt piece. That tells you you're not integrating anymore. Okay? So negative 32t squared divided by 2, right? Plus 70t. Plus, what is S sub 0? 10. All you're doing is, if you understand the concept, you're taking that step out of it where you have to do the calculation of C. Because you are giving the value, the initial value of S sub 0, you don't have to do that calculation of C. Because, yeah, if you plug in all the zeros, what are you left with? 10. 10 is going to be your C. So that's it. Clean it up. S sub t equals negative 16, which is a common coefficient. We're working in feet per second. Yeah. I think it's like negative 9.6 if you're in meters per second or something like that. And there you go. There's your two functions. So we'll do one more, but I think these are pretty straightforward. Kevin.
Will we always just get one number for AC? Or is it like function?
Usually you're just going to get one number. Because if you think about it, we've pretty much only worked with projectile motion. So we've started, all of our position functions are something squared. So if we start with something squared, your acceleration is always just a constant. Right? You can, I mean, it can be, you could end up with one more, but for the test, I'm just going to give you the, how's that? We'll keep it easy. So let's do one more. Now we know we don't need the C value because it's just, we're going to use the formula. Do one more. So let's suppose that A sub t is negative 9.8. Let's have V sub 0 of 20. And S sub 0, the initial is 0. Okay, so you have your acceleration. The first thing you can find from acceleration is velocity. Velocity is going to be the integration of negative 9.8 dt plus whatever the sub O is. Okay? So let's do it. What is the integration of negative 9.8? And then V sub O we said was, there's your velocity function.
So put in VT equals S minus 9.8 dt plus V over 0. Can we just put plus C?
Yeah. It's essentially what it is. It's just finding the C, but because we're given initial at 0, you can see, I showed you in the last problem that when you plug everything in, it ends up just being that value. So we can skip all that and just put the value in. And then the other side, the position function, of course, is the integral of the velocity plus S sub 0. Sorry. All right, what's the integration of the velocity? What did I miss? The plus 20. Hold on. Plus 20. I forgot the plus 20 when I wrote it out. Negative 9. I'm going to put negative 9.8 t squared divided by 2, and then we'll clean it up. Plus 20t plus my S sub 0, which is just 0. I'm going to clean that up. And S sub t, now you get your negative 4.9. So do you like this problem? I hope you like this problem. It should be pretty easy, right? Hopefully, if you get it. Got it. Kyle. Yeah, because if I give you the zeros, you don't even have to calculate the C. So like what I did in that first problem is showed you why it comes out to exactly that. Yeah. Yep. Not for these problems, no. I am going to give you A sub t, V sub 0, S sub 0. That's it. I know, you're all thinking this is just, there's a catch here, right?
Yeah, but that's when the catch falls.
It's a catch. No, this is it. This is it. That's all I'm doing from 6.1. I just want you to go back. And it's just reiterating that relationship between position, velocity, acceleration, right? In the other direction. That's it. It's just taking that relationship and putting it in the other direction.
This is my favorite part of this class, when everybody understands everything, so they're like, there's something wrong.
I know. And you know, I probably go, oh, you're gonna love this. It's gonna be easy, and you've like, I've lost all trust, right? It hasn't been, but I thought this one's pretty easy. That's a nice test problem. You can get this one right.
So that extra credit.
Not extra credit. This is a test problem. Now, let's do the extra credit problem. No, this one is full credit for the test. I will give you this problem on the test. You're going to get it right. No, 6.2 is the extra credit. I promise it's not going to be that hard. It's just a little more work. So 6.2, and this is the meat of where you pick up in Calc 2. Okay, that acceleration, velocity, position stuff, we kind of trickle it in, like sprinkle it in throughout the course, because especially for the engineering majors, when you take, because after this class, if you're engineering, you're going into analytical physics 1. You will literally start with those kinds of problems, derivatives and integrals of what we just did. All right? You'll jump right into that, mostly derivatives. Okay?
I've always been curious about that.
Yeah, well, the one that deals with, I always forget. Physics 1 is motion. Physics 2 is, one of them is sound waves.
I'm in analytical physics 1. It's all simple tricks like cosine.
Yeah.
Okay.
Yeah. But there is one of the, so each of the physics, you don't even have to take one. I mean, I think they make you take one after the other, but there's different types. So one of them deals with sound waves and stuff like that. One of them deals with like electricity. Okay. Here you go. Now you all know what the extra credit is, right? It is the area between two curves. Mm-hmm. What we have done so far, think about it. What we have done so far is taken a curve and found the area between the curve and the x-axis. basic integration gives you the area between the curve and the x-axis, even if the curve is below it. Right? And we found that the net, that's technically negative, and it depends on the context of the problem if you keep it negative or not. Depends on, that comes down to the context of the problem, kind of like the idea of the difference between displacement and distance, right? Whether you deal with the negative or not. Now we're going to look at the area between two curves. So I want you to think through this for a minute before I give you. It's not difficult. It's basic integration, essentially. So if I give you two curves, and this you don't have to take these notes, you're just kind of thinking through it. So here's a curve, right? So if you did, and here's A and B, okay? So if you did, let's call this one f of x and g of x. So you've done stuff like this before. If you want what's between them, well, if you integrate from A to B of f of x, what's that going to give you? That's going to give me everything in red, right? Oh, okay, I went too far. There you go. Right? Everyone agree? Now, if I integrate g of x, it's going to give me everything in green. Will be Christmassy because it's December 1st. Sorry for those who don't celebrate Christmas. I'm Italian, so red and green. Ooh. It's even the flag. So, sorry, I told you I was in a mood today. I apologize. So, I want which area though? Yeah, the one that's just red without the green, right? So I got to take the entire red area and do what? Subtract out the green area. Make sense? That's it. So the area is going to equal to, the integral from a to b of f of x minus the integral from a to b of g of x. Don't get confused if they're somewhere else on the graph. Because watch, let's suppose f of x is above the x-axis. Let's see if this formula holds. Let's suppose f of x is this nice curve above the x-axis. And g of x ends up being a curve below the x-axis. Does that change the initial formula? So let's think about that. Now, my red is my area of f of x. We good? My green is the area of g of x. Okay? Question is, do you have to change the formula, this formula that I have for area, because one of them is below? Yes or no? It's all I want you to say right now. Yes or no?
Only if you want to take the net on
Yes or no? Do you have to change this formula? Watch. Do we all agree by looking at the picture, what we're really doing is kind of adding the red and green together, correct? Does everyone agree with that? Won't that happen naturally though? Because everyone's like, yes, if you see it, because yeah, this area is going to end up being positive, right? The green area ends up being what? Automatically, when you take the integral, it's going to be negative. And guess what happens when you take a positive minus a negative? You're adding them together. So yeah, it doesn't matter. It doesn't matter where they are. It's okay that one's above and one's below. That formula holds no matter where the graphs are. Does that make sense? I just don't want you to get confused, but that you have to look at the picture and see where the graph is first. It doesn't matter if part of it's above, part of it's below. It's all taken care of in the formula. Okay? So all you need to do is, now there is a little algebra catch. I love the algebra catch. All right, you ready? I'm going to give you a problem. I'll see if you can tell me the algebra catch. Yeah, let's do this one. Is this the one I want to do? Sure. All right, you got the formula, right? I don't need to leave that up there. You're basically taking, this always works as long as you take what you would consider the upper minus the lower. All right, so I want the area of the region bounded by the graphs of f of x equaling 5 minus x squared and g of x equaling x squared minus 3. So how did I just make that problem harder? That's it. I want the area bounded by the graphs. I just took that concept, and how did I make it a little bit harder? So, bounded by the graphs. What that means is, I gave you two graphs you at least know the shape of a little bit. They're parabolas, correct? Everyone agree they're parabolas? This parabola has a minus x squared. What does that tell you? It's going down. This parabola has a positive x squared. What does that tell you? What do you need to figure out before you can even start this problem? What didn't I give you in the problem that you need to figure out on your own? The boundaries, yes. The actual boundaries, the A to B. Okay, the A to B in this particular problem is naturally occurring at the intersection. So here's my question to you. How do you find A and B if you're given two curves? I told you I was going way back to like algebra 2. You set them equal to each other. What's happening? Think about it rationally for a minute. What's happening at these 2 points? Your curves are what? They're equal. They're the exact same point. So all you have to do is set your two curves equal to each other and get your A and B before you can start. All right, so add a little piece. It's an easy piece though. Set them equal to each other. What do we get? We set them equal to each other. So the first thing, if not given to you, now if it's open curves, it'll be given to you. But if you are asked for a region bounded by curves, you have to find A and B. You're not going to come up to me and go, I can't do this problem, there's no A and B. I'm just going to say to you, then you don't get the extra credit. Right? How do we find A and B? You just set your graphs equal to each other. So, 1, find A and B. Set f of x equal to g of x. Where do they cross each other? So, we only need the A and B values, so we only need the x value. 5 minus x squared okay, just solve it. I don't know. I'm going to move everything to where the x squares are positive because I like to do that, okay? So that means I'm going to set this side at 0. I'm going to move the -5 over, and I'm going to move the 5 over as a -5. I'm going to move the negative x squared over x. So what does that give me, everybody? 2x squared minus 8. Do we agree? 2x squared minus 8. Take out, oh, you're just factoring. Take out the 2. You get x squared minus 4. Right? What are my 2x values? That's going to make that whole thing go to 0, everybody. Yeah. Yeah. So as I said, you had to go back to algebra 2 here. Oh, algebra 1, actually. Where does it equal 0? 2x squared minus 8. Take out the 2. Now I got to figure out x squared. Well, x squared minus 4 is x plus 2x minus 2. What are the two values that make it go to 0? 2 and negative 2. So what are my a's and b's? I'm going from negative 2 to 2. Now I know what I'm doing. So essentially, what does my area look like? Of, what was f of x? 5 minus x squared. I will keep it easy in that I will make sure the f of x function is the upper function in the g of x. So you're always, no matter what, you're going to do f of x minus g of x. Does that make sense? You don't have to know which one comes. But you might have to find those boundaries, though. You will likely have to find those boundaries. So you've got to figure out your a and b values by setting them equal to each other, solving for x. So 5 minus x, watch your signs. Kyle? Yes. Yes. X squared minus 3. I'm using parentheses because I want to make sure you do the signs correctly. So you have options here, by the way. You can integrate them separately. I wouldn't. These are easy to bring together and then integrate them. You know what I mean? Simplify the inside first before you do the integration. It makes it a lot easier to integrate. So what do we have? We have equals negative 2 to 2. I think that becomes 8 minus 2x squared. Check my math. Check my math there.
Yeah.
What? Yeah. I just, when you do it this way, you get 5 plus, you get 8 positive. Integrate it. Kyle? You can. So here's what happens if you integrate it separately. Then you got to do the subtractions separately. It's actually more work. We can bring these together because they all combine. Yeah. You can totally integrate it separately. It's going to lead you more steps. And here's my issue. If you have more steps, that's more likely chance of making a silly arithmetic mistake, right? Yeah. But you can totally, when we're done this, I'll show you the formula of them separate. They can be separate. They can be together. It doesn't matter. Well, I'll see if there's, yeah, I really can't even come across with any of the ones in this section. Putting them together should always be pretty easy. No, yeah. So what do we have? We have, that is 8x minus 2x cubed over 3 from negative 2 to 2. And you just got to plug in everything. It's just do the math. 8, 2 minus 2 cubed over 3. Please don't forget, when you subtract, use brackets or something. You've got, I mean, this is where the mistakes come. You forget to like distribute the negative sign, okay? So use the brackets. Then it's 8 negative 2. Honestly, this is where you'd make any mistake here, is with all these negatives. So let's go through it really carefully. And then I'll ask if anybody saw a quicker route. So what's that going to give me? 2 cubed is 8. That's 16 thirds, right? Minus negative 16 plus 16 thirds, correct? So it's 16. I'm going to multiply this by 3 over 3. So I'm going to get 96 thirds. All right. 64 thirds is the correct answer if you just do all the arithmetic right. And I'm going to ask you, did anybody, I don't know that it's really quicker. Anybody see a kind of a shortcut? Yeah. Did anybody see a shortcut? Look at your 2 original functions. Yeah, they are even functions. Does everybody see that? They're even functions, correct? So instead of doing all this work, which was fine, we did it, it's correct. You could literally, because it's an even function, when I got to here, I can use the rule for even functions. And instead of going from -2 all the way to 2, I can do half that and go from 0 to 2. As long as I do what out front? Multiply it by, yeah. This is where the even function rule comes in, if you know it. It's not an odd. Odd's even better, because then we can go like this and be done, right? What would we say if it was odd? It comes out to 0. But it's not odd. They're both even functions. It is an even function. So essentially, if you saw it was an even function, you can double half of it. What does that do? This was a lot of arithmetic with fractions. Yes. Okay. So one of the things, is it quicker? Let's see if it's quicker. Oh, I don't have to do -0 because what happens when I plug in the 0? It all goes to 0. So look at it. I have this much math work to do versus this much math work to do. 2 cubed, 8. Yeah. You still have to do 16 minus 16 thirds, so you got to take 16 times 3. Calculators. 16 times 3. Come on, it's like the last lesson of the year. 48, thank you. Which I think gives you 2 times 32 thirds. So, I mean, you can compare to math, and here, I can make it a little smaller. Doesn't matter. Did you get a different answer because you didn't apply the even function rule? Oh, thank you. Keeps wanting to erase on me. Yeah, so that's where the even function rule. And again, so this was a good review of the even odd function rule. Okay. Does it matter? No. You said it's the same answer. Okay. Do your extra credit. Or it's extra credit. I'm going to do one of those class. It's going to be very similar to that. All right. I'll give you when I do, I'm going to stop this recording so it's a separate recording. When I go through what to review for the final, I'll give you like 2 or 3 problems in the book where you have the solution to. You do. I gave them to you at the beginning of the year. I even posted it in Canvas, student solution manual to all odd problems. You can practice a couple if you want. But I think of all the extra credits, this one's pretty straightforward. It's just integration. It's just a longer integration problem. Okay?